So this is the 5 of SU5. And then 10. Oh, what do I have here? This one's wrong. Okay, that's the 5, that's the 10. Does anybody know why there's so few students? Is something wrong? Is there an exam or something?
Where's David?
Huh?
Where's David?
I know, David's not here, and...
Yatsa, I saw him earlier today.
What?
Yatsa? I saw him earlier today. That's...
Maybe he had an exam. All right, let me do one more preparatory thing. So these are SU5. SO10 has a 16. Okay, we've got, okay. Yes. Yes. Okay, I'll come right out. Bye.
Seems like he needs no space.
That's only 10.
You said that was SU5,
so yeah.
2 on the left.
On the left, that's the 5 and the 5. So, I mean, usually you write, like you write for like a number in the number bar, I mean the representation of the, whatever the other representation is called. But the thing that confuses me about his thing, I just right now guess what's a 5 star, it's going to be a different. So I don't think he's doing it. I don't know what those mean.
So what are D? What is D?
I mean, E is the electron, U is the neutrino, and D are some down quarks of different color. Right? And so because the whole point of this was to bring in or is this what he's doing? Did he say what he was doing, or did he just start writing?
You just started writing.
Okay. Then yeah, he's trying to bring color, so maybe strong into the electroweak. And so this is going to be one of the ways of doing that. So these are some representations of something. Or like these are spitter, like effectively spittery.
Okay, we've got pizza. This is, say you get to grade me, put you in a good mood, I brought pizza. So, why don't we all have some, actually? Plenty of pizza.
Thank you.
So what do your little superscript C's mean? The superscript C's?
The C?
Yeah.
Well, what you know is, of course, if you have a left-handed field, left-handed two-spinner, take the complex conjugate, multiply by sigma 2, and what you've got is a right-handed one. And the convention is to put an I or a minus I here.
No.
So that's what that means. So, the idea is that in grand unification, let's see, maybe we should turn it on.
It's turned on.
Yeah, it's been on for a little while, yeah.
Okay. In grand unification, yeah, have as much as you want. We've got tons of
You must be doing a survey today.
Yeah. In grand unification, the idea is to put all the particles of a given family into a representation or several representations of a simple Lie group, a simple compact Lie group. Simple means that there's no invariant subgroup, no non-trivial invariant subgroup. The whole group is obviously an invariant subgroup, and the identity element is an invariant subgroup. These are trivial invariant subgroups. The deal is, if you have a simple group with no invariant subgroups, then you have basically one coupling constant. And everything else is Gordon coefficients, effectively. Moreover, if your group is a group with unit determinant, all the matrices have unit determinant, then all the generators are traceless. And so not only might you have one coupling constant, but you also, all the elements, you can diagonalize a certain number of the generators, and all of the eigenvalues of those on their diagonals would have to add up to 0. So you get a kind of charge quantization geometrically. You can see that in SU5 because you've got 3 d quarks with charge minus a third, but they're conjugates, so they have charge plus a third. So altogether that's charge plus 1, charge minus 1, 0. So what that tells you, in other words, is if the neutrino is neutral, if the electric charges are color independent, then the d quark has to be minus a third the charge of the electron, which is to say plus a third the charge of the proton. In the 16, the sum of the charges is automatically 0, because for every field you have the conjugate field. So the charge conjugation isn't so clear in 16. What you can argue is that 16 is broken down first into FU5 times something, this is SO10, the group. Let me just make clear here, the group, here the grand unification group is SU5, over here it is SO10. Actually, quite curiously, SO10 was discovered before SO5. And you can see why, because all the particles go into one representation. People knew back in the 70s there either was or was not a right-handed neutrino. If there was a right-handed neutrino, then there were 16 particles. And it was not very hard, if you knew some group theory or knew where to find a good group theory book or a good group theorist, you could find that there was a group that had a 16-dimensional representation, and it was SO10. And so Harold Frisch, Peter Minkowski, and Howard Georgi actually all discovered SO10. And then when a few hours after Georgi figured out SO10, he realized that he wasn't getting a lot of charge information from this, but he realized that SU5 would work, which is a smaller group. And so he and Glashow proposed SU5 as the group of grand unification in 1974. There's plenty of pizza, okay? We've got another pizza underneath. All right, let me back up a bit and just show you that something of what's going on here. You see, you have the SU2 left acts on left-handed fields. Then you have SU3 of color, and this acts on all the quarks but none of the leptons. And then you have the U1 of hypercharge, which more or less acts on everything. And so the idea was to embed all these three into one simple group. Now, the first problem they had was that this thing was left-handed, and so what are you going to do here? You don't want a gauge group that takes a right-handed field and moves it into a left-handed field, because those fields transform differently under Lorentz transformations, and so you'd have a screw-up of Lorentz invariance. So the solution, which was really a radical solution here, let me open the second pizza. So just come forward and take off. I can think I'll have one too. There, I'll break the ice. Break the pizza. The radical solution was to embed these in a group that only acts on left-handed fields. And so what do you do then with the right-handed fields? Well, you take all the right-handed fields and make them left-handed by this thing. So for each of the right-handed, here I'm talking two-component spinners. Two-component in the sense of spin-up, spin-down components. You take R star, and by star I mean you Hermitian, you have, in other words, L is L1, L2. This is minus or plus I, sigma 2, 0 minus I 0, R1 dagger, R2 dagger. Okay? That's what I mean. So this thing makes a left-handed field. And that's what we mean by C, conjugate. We're just taking a right-handed field and making it left-handed. So once all of the fields are left-handed, you then have 15 or 16 left-handed fields, and then you act on them with the gauge bosons, and that multiplied by the generators. So you have A mu, A TA, and in other words, your D mu is D mu plus, and typically we have an I here because of the physics fetish. And so now you have a lot of generators, more than, here you have 12 generators. You need more if you're going to put them all in one big group. But they're all only acting on the left-handed fields. Okay. This, however, creates a huge problem. In other words, it's a radical solution. It's sort of like a double mastectomy, a double radical mastectomy. Now that may work in some cases, but in other cases it may be quite excessive. Anyway, I suppose that was not a very good example. Anyway, this was a radical proposition, and the problem with it is that you then have, in the same multiplet, electrons and anti-down quarks. You have up quarks and anti-up quarks, and so forth. And here you've got all the fundamental fields in the same multiplet, so you have almost any reaction is possible. And that meant that proton decay was possible. And so what people said was, well, this these gauge bosons that mediate proton decay, we're going to make them massive. And so then the rate, or the lifetime of the proton, was proportional to, I should say, the mass of the proton. Wait a minute, no, I'm sorry. mass of these new bosons, where they were called X and Y, to the fourth power divided by mass of the proton to the fifth power and alpha squared, alpha being the fine structure constant, yeah, I have another alpha being the fine structure constant of the grand unification group. Notice the reason why we have that to the fourth is that the amplitude would be 1 over mx squared, so that's the amplitude. The probability is the square of that, so the rate goes as 1 over mx or my to the fourth power. The lifetime, therefore, goes as the fourth power. You know this, you know that, you can, I'll say more about this, but you know it's got to be somewhere between fine structure electroweak and fine structure strong. So you can estimate what this is, and the estimates came out 10 to the 28th years, 10 to the 30th, 10 to the 32, and so people then built underground detectors to look for proton decay, and these detectors were basically huge bathtubs underground, but with lots of detectors that would detect photons. So the whole wall of the bathtub was detectors of photons, and the idea was if one of these protons in the water decayed, you'd pick up the photons from it. Let me see. A little more of the decays, a little more about the decays. All right, it's this page. That's funny. I thought I had. Here we go. Okay. So in SU5, for example, and I think also in SU15, SO10, we have proton, which of course is U red plus U green plus U blue, no, D blue, say. This is the proton, and then this can decay into, just leave the U red, but these two guys can go into a red conjugate boson. That is to say, there are red, green, and blue Y gauge bosons, also red, green, and blue X gauge bosons, and the conjugate ones have the anti-color. So it's basically GB goes to anti-red is essentially what's happening. And then what we have is that this goes into U red plus U red conjugate plus E conjugate. In other words, a positron. This guy can decay, in other words, into anti-red up quark and a positron. And now these two can combine to form a pi-0 meson. And so this goes into pi-0 plus E plus being EC. And of course, that's not the end of the story. This goes into gamma plus E plus. And those counters on the walls of the thing, of the bathtub, were designed to pick up the photons of pi-0 decay. And I guess for practical purposes, this pi-0 was typically, well, I mean, it could well have been at rest, or at least low momentum. And so you'd expect to see two 70 MeV gamma rays, and nothing was seen. The lifetime now is, for this decay mode, the lifetime is greater than 8.3 times 10 to the 33 years. And so that's pretty much put the conventional SU5 out of business. Let's see, what do I want to say now? On the other hand, this lifetime, you see, goes into the fourth power of these gauge bosons. So you double the gauge boson, you get a factor of 16. You make the mass of the gauge boson 4 times heavier, then you get a factor of 16 times 16, which is, I think, 256 or something like that. And so you can, by jacking this up, you can get the lifetime long enough so that we wouldn't have seen it in these detectors. Of course, these proton detectors turned out to be marvelous neutrino detectors and became useful in particle astrophysics.
I'm sorry, I didn't follow how that lifetime killed SU5. I didn't make that connection.
Yeah. Well, okay. Excellent question. Let me give you a
Sure.
a candy if you have any room for it. Let me pay the. By the way, did you all get pizza? Well, there's plenty more.
There's still like
Yeah.
They're gonna pace
Come
it
get
out.
another pizza.
They're gonna pace it out a little bit.
Pace it out a little bit. All right. All right. Also, I have to give you these forms to fill out. But all right. Let's. The answer to your question is a little bit of a long story, or a medium story, not a long story. If we want to put these guys in to a simple group with one coupling constant, then what do we expect to be happening? Well, first of all, the trace of a half G strong lambda 3 squared. Remember, this is a standard thing. Trace TATB is some constant having, depending on the representation, delta AB. That's what you do with the generators of any compactly group. And so if you add these up, what you get is twice the number of generations. I'm following Weinberg here, and of course he, instead of just doing it for one family, he does it in general. What are we going to do? G strong squared. And then for the SU2, it's trace of what he calls T3 squared, and this turns out to be 2NG G squared, where G is the coupling constant. In other words, the coupling constants here are G, GS, and G prime. And what we want to do is we want to see if we can have one coupling constant in this group that was unifying everything. And the next one is trace of what he calls Y squared, and this gives us 10 over 3 number of generations G prime squared. In other words, these are the generators of SU2 and so what do we want if we want everything to be the same? Well, if it's all one coupling constant, then we'd have to have GS squared equals G squared equals 5/3 G prime squared, because we just have that would be what we need for one coupling constant for a simple group. Well, these numbers, of course, don't work, because this one is a strong interaction coupling constant, and it's a strong interaction, so it's big. These guys are of the order of, they're electroweak coupling constants. Okay, well, and in fact, there's an angle which Weinberg, in a fit of humility, caused sine theta, left out the W. One has to admire that. Anyway, sine squared theta, weak or whatever, is G prime squared over G squared plus G prime squared. And this is 3/8. That is to say, it's 3/8 if we adopt this relation here, the 5/3. And 3/8, of course, is 0.375. The actual value of sine squared theta is 0.231, or at least that was the value when Weinberg wrote volume 2 of quantum field theory. So these, I mean, I'd have been happy with such agreement, but Weinberg isn't, and in fact, other people aren't either. So the question is, how do you arrange for these two to be plausibly the same? Well, what comes to the rescue, of course, is that you say, you already know that the protons aren't decaying. I mean, we're alive, okay? So the proton decay rate can't be too high, or we'd all die of radiation poisoning. And so they knew the lifetime of the proton was quite long, of the order of the age of the universe, or longer. And I guess that meant that the original experiments for proton decay, which were done in Japan and Ohio and perhaps other places, I guess these were started with great enthusiasm. But and then they did neutrino physics. Anyway, I'm sorry, I've gone off on a tangent. Yeah. Anyway, people knew that this X and My was going to have to be pretty big, for sure. And the question was, how big? Well, way beyond ordinary energies. And so the unification doesn't really occur until you're beyond, you're at an energy scale that's at least this big, if not bigger. In other words, an energy scale at which the X and Y gauge bosons are light. So that means that we're dealing with running coupling constants. And you remember how running coupling constants run. They're, in fact, one can write down these equations. Mu dD mu of G strong of mu, well, this is G strong cubed of mu divided by 4 pi squared, and then we have 11 over 4 minus, and the number of mg over 3. I'm a little puzzled. I thought that would have been the number of fermions. Maybe he's factored the number of fermions in. All right, let me just follow what Weinberg has without being too careful with all the details. The SU2 one is then minus G cubed of mu over 4 pi squared, 11 over 6 minus mg over 3, and then u d by d mu, g prime of mu is minus g prime cubed of mu, 4 pi squared, and now this thing is minus 5 ng over 9. Notice that this one is growing. That's the fact we saw when we did the running coupling constants, that the U1 case grew, but that the others tended to decrease as the energy goes up. If you integrate these equations, and what happens is you get dg over g is mu d mu, dg over g cubed, I guess, is d mu, and dg over g cubed integrates to 1 over g squared, and so you get the equations then 1 over g squared, gs squared of mu is 1 over gs squared of mu at the unification scale minus 1 over 8 pi squared 11 minus 4 number of generations over 3, and then a log term m over mu. Of course, the log comes from d mu over mu integrates to log mu. You get that equation, you get 1 over g squared of mu is 1 over g squared at unification minus 1 over 8 pi squared, 22 over 3 minus 4, and g over 3 log m over mu. And then finally, 1 over g prime squared of mu is 1 over g prime squared of m minus 1 over 8 pi squared times minus 20 ng over 9 log m. Okay, so you get these three. And so then we reinterpret this relation. We say this is what we want to happen at m, the high energy. In other words, we want gs squared at m equal to g squared at m equal to 5/3 g prime squared at m. And now, fiddling with these, subtracting one from the other, canceling. Anyway, a little bit of high school algebra, we get 1 over gs squared of mu minus 1 over g squared of mu equals minus 11 over 24 pi squared log m over mu. Another equation that we get is 1 over g squared of mu minus 3 over 5 g prime squared of mu equals minus 11 over 12 pi squared log m over mu. And now you take the ratio of these two equations, and what you find is sine squared of theta is 1/6 plus 5e squared at mz. In other words, we're setting mu equal to the mass of the z. Okay, now this is something that's much more realistic. And so this is something plausible. And one also extracts the rule, the log of m over mz is 4 pi squared over 11e squared times 1 minus 8e squared at mz divided by 3g squared s of mz. Okay, well these things are measured in experiments, and in fact there were experiments at LEP which were available when Weinberg was writing this, and so you compute these things, and that gives you an idea of how big this is. And that basically the estimate there was that M should be about 1.1 times 10 to the 15th GeV. So that's basically what the result is. And this is basically independent of SU5. This is sort of arbitrary grain unification because there wasn't any restriction to SU5 or SO10. And so that tells you what M is. That tells you what the lifetime might be. And so what does this give you? This gives you two things. First of all, these are these famous, unfortunately there's no diagram here, but basically if you're plotting the various alphas with energy, the strong one goes down, that one goes down, this one comes up, and at around 10 to the 15th, they don't quite meet, but they're in the ballpark. They're quasi-close. So that was encouraging, and that meant that there was some basic logic to this. But then you plot, now you know what M is, mx, my, 10 to the 15th. That's the answer to your question. You then plug it into that formula over there, and I might as well walk back here to where the pizza is. You plug it into this formula, and so you get 10 to the 60th, I guess, here. And you know what the alpha is, or at least, and you can figure out what, what energy scale you're doing this. Presumably you're doing this at very low energies because the proton is at low energy decay. And then you obviously know the mass of the proton in many digits. You compute what this is, and it was, let me see if, yeah, it was, this gave 10 to the 32 years. And as I said, we've got something much more than 10 to the 33. And of course, if the lifetime is 10 to the 32, then you build a big detector. You expect a few observations even before you've measured few observations at big enough tank of water. You expect to get a certain number depending on what the lifetime is. And so this basically was ruled out. What came to the rescue then was supersymmetry. And I'm going to be talking about supersymmetry on Thursday. The idea there is that for every particle, you add another particle with a spin that differs from the spin of the first particle by a half. So if for every fermion you would have a scalar particle, for every gauge boson you'd have a spinner, for the graviton you'd have a gravitino spin 3/2. That basically is the idea. What happens then, since you've got all these extra particles, and you remember when you do loops, you have an extra minus sign with fermion loops. And so in these various loop diagrams which cause divergences, the supersymmetry gives you an extra diagram with a minus sign. And so the evolution of all these equations that give you the evolution, they go more slowly. And so now you're saying, well, they actually do intersect better at 10 to the 16th GeV. So you've got an extra factor of 10. You put that into toy, that gives you a factor of 10 to the 4. And, yeah, 10 to the 4. So it goes up to higher values. On the other hand, the fact that we haven't gotten any decays at all, I don't know. I'm afraid I haven't looked into the details of how good so what the current status is of the lifetime of the proton in various supersymmetric models. Of course, what you have in these supersymmetric models, since you've doubled the number of particles, you've got all sorts of new coupling constants, and so the freedom in the supersymmetric theory is absolutely extraordinary. And all the experimental evidence so far has been negative. I remember I once, visiting Berkeley, saw an advertisement for a conference. It was Supersymmetry Confronts Experiment. Somebody in pencil had written, Experiment 10, Supersymmetry 0. And that's still the situation. On the other hand, the LHC is now operating, and they're slowly ramping up the energy to, they expect to get to 13 TeV, but sometime in June, and by June, July, or August, we may have evidence for supersymmetry. So it's an experimental question. Unknown. All right, look, why don't you guys fill out these forms? Yes, is that a question?
Yeah.
Yes, question.
So we have all the fields in this
Right, hold, let me get you a candy. It's better that I throw you a candy than a piece of pizza. Okay, what's the question?
So we have all the fields in this vectorized form.
In the SO10, in the 16.
All the other ones. So what is the equation motion for these fields, for these things?
Good question. Well, what you do, of course, is you write down the action. The action will be F mu nu squared, where the F mu nu. See, we have actually, for SU5, we have 24 gauge fields. We had 12, and we had an extra, we have 12, we have an extra 12, and the reason we have 12 is that we have 3 x's, 3 y's, 3x conjugate, 3y conjugate, so that's altogether 12. So now you have, and these are then 5 by 5 matrices. So your F mu nu is, of course, just the covariant, the commutator of the covariant derivatives. Okay? Then you take the trace of F mu nu, and that's part of the action with a suitable coupling constant. Then, of course, you take, let's switch to SO10 for a second, because then I only have one field. So suppose psi is the 16 of SO10, then the thing would be psi bar, gamma mu, d mu psi. Okay? All right. So this is the action then for the fermions. This is each family. You have 3 families, of course. This is the action for the gauge bosons. Then, of course, you've got to somehow account for the fact that this mass is 10 to the 15 or 10 to the 16 GeV. They're not mass 0. If you just had these terms, you'd have mass 0 for everything. So what you do is you invoke the standard Higgs mechanism, and you say you have certain Higgs fields, whereas in the ordinary standard model, the Higgs fields were an electroweak doublet, an SU2 left doublet. In the case of SU5 and SO10, they're more complicated multiplets of fields, because the fields that transform irreducibly under SU5 and SO10 are of different dimensions, 5, 10, and so forth, 16, and there I think is a 45 and so forth. So you consider what Higgs representations you want. You then make things that are invariant under the total group, SU5 or SO10. You make those polynomials up to fourth order in the Higgs fields, and they find a minimum somewhere. They form a mean value in the vacuum, and that mean value gives you symmetry breaking of the SU5 or the SO10 at 10 to the 15th or 10 to the 16th GeV. The equations of motion, the classical equations of motion, come from saying that the total action, which is this plus the Higgs terms, is stationary to first order in small variations. What one normally does is you put this into a path integral, and you integrate over all gauges, so you do the Faddeev pop-up trick, fixing the gauge, and do perturbation theory. So that's basically the scheme. So it's like any gauge theory, it's just a bigger gauge theory. One of the big problems that was discovered back in the 70s was that if you don't have supersymmetry, I described how nicely these coupling constants vary with energy. The problem is that the divergence of the Higgs, the divergence of the scalar fields is quadratic. And that leads to a pretty rapid variation of say, the mass of the Higgs boson. In particular, you've got you have these various Higgs bosons that break things up at 10 to the 15th, but then you've got some other Higgs bosons left around that form very tiny mean values in the vacuum, only 246 GeV. Okay? And those guys are just invisible at gut energies, but they give you the ordinary breaking of electroweak symmetry into the weak interactions and the electromagnetic interactions at ordinary energies. A few hundred GeV, say, that change, the symmetry goes away, and we have just, we look up and we see photons rather than W's and Z's from the fluorescent lights. And so one of the problems is if you have quadratic divergences and the mass of the Higgs field gallops instead of just canters or walks as the energy changes, then you've got to somehow figure out how you fine-tune things, numbers that are of the order of 10 to the 15th. These are some of the constants in, even after you've renormalized so that you've gotten rid of the actual infinities and you just have these finite numbers in your Lagrangian or your action, you've still got to cancel these terms that are of order 10 to the 15th. You've got to cancel them so that they are accurate to 100 or 200 GeV within 10 to the 15th, and moreover, the damn thing runs. And so that's called fine-tuning. That's alleviated to some extent with supersymmetry because the divergences are less instead of being. I think everything's logarithmic in suitably supersymmetric theory. In fact, there's one supersymmetric theory, n equals 4 Yang-Mills. It's actually ultraviolet finite. It'd be nice if it was realistic. That's the kind of theory I like. Okay, did I answer your question more or less?
Yeah, kind of.
Yes.
This is more of a practical question. I guess you've commented that it's very difficult to do.
That what?
You've commented that it's very difficult to do useful calculations with QCD.
Mm-hmm.
I would think going to this higher, bigger, larger groups and more that it's much more difficult even to do useful calculations on SU5 and SO10.
Right. The thing about QCD that drives people nuts is that the coupling is strong.
Okay.
So you have to calculate as many loops as you possibly can.
Okay.
As you go to high energy, the coupling constant goes down, but it only goes down logarithmically with energy.
Okay.
Did I?
I'm good.
Why don't I just give you another
slice of pizza?
Slice of pizza instead of screwing around with the candy.
Yeah.
Okay. I did want to show you one more thing, the Glauber
Oh, that's right. I'm sorry.
identity, but the trouble is, you've got to. How long does it take you to fill these out? 5 minutes?
Less than 5 minutes.
Hmm?
Less than 5 minutes.
All right. So let me do the Glauber thing, and then I'll show you. This is. I'm skipping all of the Schwartz stuff on QCD. He does QCD for a living, and I thought those chapters were just too much. However, you can say something. So let's consider quantum electrodynamics to start with. Well, here's what we're going to do. We're going to have the electromagnetic field quantized. We're going to make the current, though, classical. So this is quantum electrodynamics with classical electrons. Okay. So the S matrix, of course, is, and I'm doing sort of the operator lingo. The S matrix is E to the I integral interaction Lagrangian time ordered. And while you're at it, we can normally order it just to remove some spurious divergences. Okay. So what is this? Well, this is, and let's forget about the normal ordering. I don't think that's going to play much of a role. This is integral then J mu, A mu, D forth X, and the B and E there for the coupling constant. Okay, but now we're having this classical. This is quantized, and the time-ordered product part is still serious. Okay. But a long time ago, Glauber proved a simple identity, which is e to the A, e to the B, is e to the A plus B plus a half the commutator of A with B if the commutator of A with B commutes with A and commutes with B. And those of you who have, let's see, there are various quantum mechanics books. This is proved in one of them. It's the one written, I think it's the author is French, isn't
The 2-volume one, the thick.
it? The what?
The 2-volume quantum mechanics.
It may be proven in there. All right. Anyway, it's not that hard to prove, but let me skip the proof at the moment. Let's now consider two time slices. So what we would have then is e to the j mu a mu e to the j mu a mu prime. So we don't have to worry about the classical current commuting with anything, but with itself. We have to worry about these guys. On the other hand, this A mu is a linear combination of annihilation creation operators. So if we imagine this is A and this is B, the commutator of these two is a C number. In other words, it's some complex number. So we can obviously say that this is e to the j mu A mu plus, well, maybe actually, this is at a different time. So I'll call it J nu a nu. Well, how many nus here? Okay. Plus a commutator. But now we have the, what is the commutator? Well, this first of all, there are i's in both places. And it's then the commutator of j mu a mu with j nu a nu. And this is, let me factor out the i's, because the i's are just two i's give you a real number, -1. This is Hermitian, and that's Hermitian. And so the commutator of two Hermitian operators is anti-Hermitian. So in other words, the commutator of H with H prime adjoint is, of course, the commutator of H prime with H, because each is Hermitian, and that's minus H prime. So this extra term that we add here, plus I squared JA prime, this thing is anti-Hermitian, and moreover, it's a C number, so it's an imaginary number. So this part is real, this part is anti-Hermitian, this complex number, the only anti-Hermitian complex numbers are the imaginary numbers. In other words, this is a phase. And so the actual S matrix then has a very simple form. It's I.E. integral J mu A mu d4 x apart from a phase, e to the I phi. Moreover, this is exact. And you can either normally order it or not as taste goes. Moreover, an exponential of, this is Hermitian, an exponential of an anti-Hermitian linear combination of creation and annihilation operators is automatically what Glashow called a displacement operator. In other words, it takes you from your vacuum to a coherent state. So what this means then is that arbitrary radiation of quantum radiation from a classical current gives you a coherent state of some kind. And the argument of the coherent state is whatever E times the integral is. Of course, you then, if you want the amplitude for each momentum, you expand this in terms of its Fourier components, do the space integral, and you have the answer there. All right, I better quit pretty soon. Okay, so that, by the way, gives you also some idea of, this gives you a poor man's laser. A poor man's laser then is some classical current that radiates, and you then get a coherent state. But of course, the real point of a laser is that the momentum is the same. Those are the photons. Now, the reason why I thought of showing you this is that if we go from electrodynamics to quantum thermodynamics, the difference would be that we would have a J mu A, AA mu, and now we would have the 8 gauge bosons of QCD, or SU3 color. And if we imagine that these currents here were classical, as opposed to quantum, and of course these are the, well, these are the, these are the various colored currents. So what am I trying to say? If one treats these classically, of course that's not exact, but it wasn't exact in the electric case either. But if you imagine treating them that as a first approximation, then you get that the radiation of gluons in a collision is effectively a coherent state of gluons. Because of course these AAs are going to commute with each other. And so you have e to the I, G, J mu A mu A, d4 x. You go through the same razzmatazz, it's a phase. And so the exact answer then is something like that. So you expect coherent states of gluons coming out. And I guess the next step is to say, well, these JAs that come out aren't arbitrary. They're one may take colorless combinations. Anyway, this is somehow related to jets. I thought the thing was very clearly and simply related. Now I'm not quite sure how simply or how. But anyway, this is more or less true. All right. So why don't we cut this off? You guys fill this out, and let's see. You're the TA. Why don't you arrange to have this submitted to the.
Okay.
Why don't you turn the thing off?
Okay.
Have it